right, good morning, ladies and gentlemen. Today we're going to talk about energy in a spring. So let's first look. So I got this thing up here. We're going to call this our toolbox, right, for energy. All the equations and stuff we've really talked about up to this point. Well, we have our kinetic energy equation. We have our gravitational potential energy equation. We have our work energy theorem equation. And then we have our equation to calculate the total energy in a system. And our goal today is we're going to add two more equations to this toolbox. Well, let's get started. So, springs. Everybody's seen a spring before, right? A spring is something that is stretchable, right? It's elastic and is used in everyday objects. Right? Here's a spring. It stretches, right? It's elastic. That's a spring. Now, when dealing with springs, there's this law that we're going to come across. It's called Hooke's law. And what Hooke's law says is that it describes to us, right? So it tells us the relationship between the force, right? Between the force being applied to our unstretched spring. So what does this say? This says that there must be a force being applied to this spring that's causing it either to stretch or what we call compress. That's when you push things, when you push it together. So what can we get from this? Well, we can get from this that the more you stretch out the spring, greater the force that's needed. And the more you compress a spring, as well, greater the force needed. So what is this telling us? To either stretch this spring out or compress it, push it together, there's going to be this force that is applied. We're going to be applying this force. And we're going to call this the spring force. The spring force. F sub S, our spring force. And so now this law, right, Hooke's law, there's an equation that goes with it. The spring force is equal to K times X. K times X. Well, if you look on your reference table, page 6, you know that this K is your spring constant. And what I mean by spring constant is this describes the stiffness of the spring. And you know that this X is going to be the displacement, right? The change in how far that spring was stretched out or compressed. So let's see a little diagram of what we're going to be dealing with. So pretend this is a ceiling. I'm hanging a spring down from the ceiling, and our spring is just sitting there. Well, this position we call equilibrium. So we're going to say that this is when x is equal to 0. When x is equal to 0. Well, say I put a mass on that spring. Well, we notice that the spring stretches out. What stretches out? Some distance from the equilibrium, right? Because our equilibrium is here. Well, the way it stretches out, this is going to be our x. This is the displacement, right? How far it's stretched out. And if it is stretched out some x, right, some distance, we then just have some force, right, just our spring force, Fs. Well, what happens if I have a larger mass on there and it causes the spring to stretch out twice as far now, right? So here's still our equilibrium line, but our distance now is 2 times, it's stretched out 2 times as great as it was in our equilibrium picture. So now we'll just have some force of 2 Fs. Now what this is showing, guys, what this is showing is the relationship between force and the displacement, how far it is compressed or how far that it is stretched from equilibrium. Let's do a picture of it being compressed. So here's my spring. Right here, this is going to be considered equilibrium right here. We'll say I compress the spring, so I push it together. And now our spring top goes here. Well, this right here, that is your X. That is your X. That's how much it was compressed. That's the displacement from where it started. So still, to do that, you're going to need some force Fs. Well, say I want to compress it even more. I apply even a larger force on it. Well, our equilibrium is still here, so we can tell that now it's increased by 2 times. 2 times. That's a 2. I'm sorry, that's not very clear 2, but that's a 2, which means that we have 2 times the spring force being applied to compress it. Right? This is stretching out. This is compressed. Now, what does this tell us about the relationship? Well, let's come up here. Let's talk about relationships real quick. If I increase X, Fs increases. This is a direct relationship. If I triple X, well then Fs is tripled, right? Here's an example of it, right? That's a direct relationship between the two. So this is Hooke's law, right? This tells us and helps us analyze the force being applied to this spring. Now, coming through here, let's just mess with our units real quick. Our units for, and I can actually slide this up. So if we have our equation, right, Hooke's law equation, Fs equals K times X, our unit for force is newtons. Our units for the constant are going to be newtons per meter. And our units for distance is meters. Right? So it's very important that we remember that the K, our spring constant, is newtons per meter. The unit for force is still newtons. It's always newtons. It's always been newtons. And our unit for distance is meters. Good. All right. Now, let's talk a little bit about graphs, right? Let's talk about graphs. So we're going to draw a little graph here, right? We're going to have our graph, boom, boom. We have our distance down here, our force on the y. So here's a graph of force versus distance, right? And say I have some line that looks like this. Well, what can we tell from this graph? What can we tell from this graph, right? And this is a graph, right? It will obviously express to you about springs, right? This is a graph that's going to be about a spring. And what can we get from this? Well, the first thing we can get is that this tells us about the force being applied. right? We can see, well, at this distance, how much force was being applied, right? Just by reading the graph like we've always learned and we've always done. Well, we can also, if we take the slope of this graph, we get something. We can get something from the slope of this graph. Well, we know that taking the slope is just the change in y over the change in x, which look what's on the y. So force is on the y, and we're dealing with spring. So that's Fs is on the y. Our distance is on the x. So Fs over x. Well, does that look familiar? Right? Would you be able to find that from somewhere? Well, let's look at this equation. Let's look at Hooke's law equation. If I divide by x, I divide by x. Well, k equals Fs over x. So the slope of this line, right? So the slope gives us the spring constant, k. So the slope will give us the spring constant. What gives us the spring constant, k. All right, well, now that's not all. That's not all that this is going to give us. We can also do, I hope you guys remember, area under the curve. Area under the curve. Well, area under the curve, let's see what it's going to give us. Well, the area of a right triangle is 1/2 base times height. So 1/2, our base is distance. Our height is going to be force. Well, force times distance gives us work. So area under the curve of a force versus distance graph will give you work. And guys, these are just things we need to make note of. If we have a force versus distance graph, and we're dealing with a spring, well, the slope is going to be the spring constant. If we are trying to find how much work is done on the spring, we then have to do area under the curve. So let me just grab a quick color real quick and we'll highlight the specific, most important things we just talked about. Well, we talked about that area under the curve gives you work. The slope is going to give you k, the spring constant. And then this tells us about the force being applied. Right? So that's everything that this graph can tell us, right, when dealing with springs. And you can find how much work is done on the spring. You can find how stiff is the spring by finding the spring constant. So let's go back here. We just added another equation to our toolbox. We have that F sub s is equal to kx, Hooke's law. All right, and so we have one more left. Let me just focus that in real quick for you guys. All right. So we have one equation left. So our last thing we're going to talk about dealing with springs is going to be the potential energy of a spring. So we call that elastic potential energy. Now I know what you guys are thinking. You're like, oh, well, we've already dealt with potential energy. Yes, we have, but that was for gravitation, right? The gravitational potential energy. Now we're going to do the elastic potential energy. And well, you may ask me, well, what is elastic potential energy? Well, still, it's potential energy, but it's the stored energy in a spring. So how much of that stored energy is in a spring now? We're not dealing with objects, we're dealing with springs. And our very important equation for elastic potential energy is P E equals 1/2 kx squared. And we're going to put a little sub s there for spring. So the potential energy in a spring is 1/2 kx squared. Our units for elastic potential energy is still joules. Remember, all energy is joules. K is still your spring constant. And those units are newtons per meter. And X is still going to be your displacement. How far has it stretched? And that's going to be in meters. Right? And you can even make a little note. When we talk about displacement, we say, how far has it stretched from equilibrium? Right? How far has it stretched or compressed? Because you can also push springs together from equilibrium. That's what you can say for the displacement, or I have you thinking about it for the displacement. So what this says is, if I have my springs here, I got a spring sitting here, is stretched some certain amount. It has potential energy in that spring. That spring has potential energy. Well, it doesn't matter if it's stretched out or it's compressed. It has potential energy in that spring. There's potential energy. It's being pushed. It has a stiffness, a spring constant, and it has some distance that's being compressed or some distance it's being stretched out. It has to be either compressed or stretched out to have a potential energy, to have that energy. All right, ladies and gentlemen, please watch this video as many times as you need to. My next video will have a couple example problems for you guys to take a look at. Have a good day.